Okay, so we've survived sampling distributions for proportions, and we've also survived confidence intervals for proportions, and specifically we've only done one sample. And so now we're going to talk about a new type of procedure. Now, confidence intervals are one of the two most common types of statistical inference. We use a confidence interval when our goal is to estimate a population parameter. Now, the second most common type of inference is called significance testing. So I'm going to put that here, significance testing. Now, this is a formal procedure for comparing observed data with the claim, otherwise known as the hypothesis. Hypothesis, there we go, whose truth we want to assess. The claim is a statement about a parameter, and we know that so far the only parameter we've dealt with is P, which is the population proportion. And we express the results of a significance test in terms of a probability that measures how well the data and the claim agree. That's what we call the p-value, which we'll get into below. Now, the statement that is being tested is called the null hypothesis. And our little nickname for it is going to be the HO. Now, the significance test is designed to assess the strength of the evidence against the null hypothesis. Usually the null hypothesis is a statement of no effect, no difference, or no change from historical values. So we believe that P equals this just based on our empirical observations, or if we have collected data in the past. Now, the claim about the population which we are trying to find evidence for is called the alternative hypothesis. So we have the HO and we have the HA. Now, usually the alternative hypothesis is a statement of an effect or a difference or a change that exists from historical values. So the HO is what we believe is true, the HA is what we're trying to find evidence for. Now, in order to assess how far the estimate is from the parameter, we standardize the estimate using the general formula. Now, you just saw standardization. The only way that we've learned to standardize so far is a z-score. And so this idea is going to kind of trickle in through the rest of this unit. So when we write our hypotheses, we generally do this. We say the HO is in terms of the parameter, P equals a value. And then we say the HA is that P is greater than, less than, or not equal to whatever this correct, or not correct value, but whatever this estimate is assumed to be about the population parameter. So we do the HO and we do the HA. Now, in order to find a test statistic, we're going to use this here. So I'm going to break this up. So in order to find our test statistic here, because it's proportions, we're going to use a z. We just do the point estimate minus the parameter divided by the standard error of the parameter. I'm going to put just para for there. So this is our procedure here. We assume that the population proportion is this just based on historical context, but we might believe that it's different, it's less than, it's greater than, or it's not equal to. And so the way we find that is we take a sample and we calculate the sample proportion there, and then we standardize. So assuming the null hypothesis is true, we can create this distribution here, or a picture of this distribution, and try to see how likely our outcome is. Now, the way we talk about how likely it is called the p-value. And the p-value of a test is the probability that we would get this sample, or one more extreme, if the null hypothesis is true. The smaller the p-value, the stronger the evidence against the null hypothesis provided by the data. If the p-value is small or smaller than alpha, we say the data are statistically significant at level alpha. In general, we use alpha of 0.05 unless otherwise stated. So normally we're looking here at the HO and the HA with alpha of 0.05 unless it tells us to do something different. Now, the way we interpret the p-value is assuming the null hypothesis is true, the probability of obtaining our sample or test statistic, or a more extreme value, is this probability here. So we have two different types of tests, one called a one-tailed test and one called a two-tailed test. Now, for this first one here, I'm going to do a less than. So if I'm trying to find evidence that for the proportion to be less than, so our HA is saying that the proportion is less than this, I'm essentially going to find this z star, right? It depends on our level of confidence, alpha and the level of confidence are very similar. So for example, alpha of 0.05 is essentially with 95% confidence. And so with 95% confidence, this z star becomes something like 1.96. And we're just looking to see, does our observation fall in what we call the rejection region? Now, if it falls here, it is totally possible to happen. So assuming that our distribution is centered here at P, the population proportion, it is totally possible that our sample could occur or something more extreme. It's possible, it just might not be a high likelihood of it happening. So that's the idea here of this p-value. So that's the first type of one-tailed test you can have. And if you can have a less than, you can also definitely have a greater than. So this would be saying that the alternative hypothesis is saying the proportion is greater than what we assume to be true. So again, you would find your z star value, and since it's a greater than, you would find the area to the right, assuming that the null hypothesis, the population proportion, is here. So we're just trying to see, is it possible that our test statistic could happen here or more extreme than this critical cutoff value? And then the last type of hypothesis test we can have is what is called a two-tailed test, or what we call a difference. Now, we assume we are centered here at P, but saying there's a difference would either mean that it's greater than or that it's less than the critical values here. So you would have a z star below and you'd have a z star above, and we're just trying to see, is our sample completely different than what we believe to be true about this population proportion? So this is when the alternative says P is not equal to. So all of these are written as Haas, right? These are the alternative hypotheses. Assuming the null hypothesis is true, we say that the population proportion equals some value, which we can see in these different distributions, is the center of these different distributions. So we're just looking for some type of evidence that would suggest that it is totally possible to achieve our sample or something more extreme with this probability. And again, in order to calculate this probability, we would need the sampling distribution to be approximately normal. So that'll just take us here to this new procedure. When we conduct a hypothesis test, we're going to use phantoms. So for a confidence interval, we panic. For a hypothesis test, we use phantoms. Now, again, you could do the state, plan, do, conclude, and these are, the first two are the state, next two are the plan, next two are the do, last two are the conclude. So it's just up to however your teacher teaches it, but for my students, we're going to be using the phantoms model. So the P remains the same, the parameter, the true population proportion of. Then we have to form our set of hypotheses. And so we would have the HO, the null hypothesis, which says the true proportion is this value, against what we're trying to test, the claim here, the alternative, which says that actually no, the proportion is less than, the proportion is greater than, or the proportion is not equal to. And then we include our alpha level here, which is usually stated in the problem. And if it's not stated, we're just going to use 5% as our alpha value. Next up, we need to check our conditions, and thankfully for us, the conditions haven't changed. So we're looking that it is stated random, we're looking that it's independent, and we're looking that it's approximately normal by large counts. If our conditions are met, we'll use a one-sample z test for a proportion. Again, how many samples, z or t, and what are we testing for? We are then able to produce this test statistic here, this z value. Again, here's our sample statistic. Here is the parameter, and here is the standard deviation of the parameter. So notice here, we are checking the parameter instead of the statistic, because in confidence intervals, we didn't know the truth. We were trying to guesstimate the truth. With hypothesis testing, we're assuming this is the truth based on the context given to us. So because we assume this is the parameter, this is information about the population, we're now checking our conditions with the parameter. We are checking the test statistic with the parameter. And actually, you might be asking yourself, well, why does this formula feel familiar? Because z, right, a z-score we know was x minus mu over sigma. X being our observation, here our sample proportion, p naught, which we know the mu of p hat would be p, and then the sigma of the sampling distribution would be p times 1 minus p over n. So you notice these two parameters here look very similar here, so we're assuming we know information about the population. Next up, we obtain the p-value by doing a probability statement, very similar to what we've done when we've always done the normal distribution calculations. Z is less than, Z is greater than, or if it's not equal to, we do 2 times the probability of Z being less than, and just to go back to that, here's the probability it's less than, here's the probability it's greater than. So if I'm doing a two-tailed t-test, I would only need to find the area of one of these and then multiply it by 2. And then the last thing here, some fun catchphrases. If the P is low, reject the hoe. Or if the P is high, we cannot deny. And so then we would either have sufficient evidence if we reject, or we would not have sufficient evidence. Now, something to note here is that these are always in terms of the null. So let's actually write that in, is that these are in terms of the null, right? We either reject the null hypothesis or we don't have enough evidence to reject the null hypothesis. So make a decision. Actually, this is based on the hoe, and then state the conclusion. This is in context of the ha. Kind of, sort of. So basically, we have sufficient evidence to claim the ha is this, or we do not have sufficient evidence to claim the ha is this. So we either reject the hoe or fail to reject the hoe. We never accept the alternative or fail to accept the alternative. So we are making a decision with respect to the hoe. So let's actually take, let's go ahead and do an example, but I'm going to stop this video so you all can enjoy me not rambling for about 30 seconds.